Section 15, fuel pump electrical circuits. First thing you want to understand with fuel pumps, computer-controlled fuel pump circuits, and this is the majority of them work this way. You have a computer that controls a pump relay. That fuel pump relay is going to control the fuel pump. This is based on two inputs. First input, obviously, the RPM. Cam crank signal. You need to have an RPM signal for the computer to run this fuel pump relay. It's a safety issue. If the vehicle stalls, when you get into an accident, you sever a fuel line, the engine stalls, we need the pump to shut off. So we base it off of RPM. If there's no RPM signal, fuel pump's not going to turn on. The other input that's involved would be the initial key on. The initial key on. We can call this a wake-up signal if you want to. When you first turn the key on, computer comes to life. It's going to run the fuel pump for about 2 seconds. It's known as your prime, and then shuts the pump back off until we receive an RPM signal. So just an introduction to fuel pump electrical, and that's what page 2 at the top is talking about. So it is a safety feature that RPM must be present for a fuel pump to maintain the on position. Okay? On some of the early models, Toyota in particular, they used that 7-wire vane airflow meter. And if you remember in a previous discussion, we talked about that vane airflow switch being used as a fuel pump cutoff. And that was essentially doing the same thing. So excluding the 7-wire Toyota that you can look at in the airflow sensor section in my book. I have that in there. Excluding that one, we're talking about all the other ones that are computer controlled. I have some common components I've listed up here, and this by no means is most of the cars. This is just our domestics. There's so many different designs out there. I just kind of picked out some things you want to look for, and there's going to be similarities with each of these. Starting with the Chrysler ASD relay. ASD stands for auto shutdown. Provides power to the fuel pump, O2 heater, ignition coil, injectors, alternator field. That would be the brushes for the alternator. And newer systems are going to separate the ASD and fuel pump relay. So let's look at figure 3. And this shows just a generic picture of that ASD circuit. So if you look at this generic diagram, you can see that computer's controlling the ground right here. This would be a ground side switch coil. When that coil gets a ground, it's going to make a magnetic field, and it's going to close this switch. And when that switch closes, it's going to provide power to all of these components, as well as power part of the computer board. Now, the reason I have this one in there is, in particular, when it comes to no start diagnosis and when you have no spark. And what Chrysler did is the ignition coils are on this circuit. And so it's kind of different than some of the cars, because part of a no start diagnosis on an ignition coil would be turn the key on and check for power on the ignition coil. There should be power there. And what you'll find on these Chryslers is when you turn the key on and you go under the hood and set up either your test light or voltmeter and you check for power on this ignition coil, there will be no power on that coil. And the car doesn't start, so you think you're on the right track, that you have a blown fuse or some kind of wiring problem, and it's not. The ignition coil is run off the same circuit as the fuel pump. So is it normal to have power to the fuel pump with just the key on? And the answer is no, it's not. Yeah, you'll get a 2-second prime, but after that, without an RPM signal, you're not going to have power to that ignition coil either. So it can definitely be misleading. And so what you could have happen is, let's say, for example, that you have a crank sensor signal that is not there. And depending on how you approach this diagnosis, you you may have started at the ignition coil and found that there was no spark on this engine. Obviously, with no crank signal, we're going to have no spark. So we start at the coil and we do our checks on the coil, and what we find on this ignition coil is our main power coming in. This one going to the computer to control the ground, the control side. This would be your power side. This would be your control. That you got 0 volts on your feed to your ignition coil. Cranking the engine over and you still have 0 volts on that ignition coil and you have no spark. So you can see where this could mess you up if you weren't aware that the fuel pump circuit is the same circuit that powers the ignition coil. And so again, on this car, you would start chasing power feed problems to the coil if you didn't realize the circuit design. I've seen other cars this way too, so be careful with it. You could have a system like this where you have a crank sensor problem that can cause no power to the ignition coil, and this would be for all the Chryslers. On the newer designs, they really didn't change anything. What they did was take the ASD relay and they added a fuel pump relay to it. So you have 2 separate relays, but the thing is, these 2 relays and the control sides of the relays themselves went back to the PCM, and there was only one driver. So yeah, they separated the relays and separated these. So what you'd have is maybe the fuel pump and the fuel injectors together over here, have the fuel pump and injectors, and on this relay you'd have your coil, your O2, and your alternator. So basically they separated the loads, but if you look at the circuit design, I'm not drawing all of it, if you looked at the circuit design, there was only one driver. So when this circuit turned on and was given a ground, both relays were energized together, and so essentially you still have the same thing. You have the same characteristics. If you lose a crank signal on this system, you're not going to have power to an ignition coil. So why did I pick this one? I picked this one to show you that variable with the ignition coil with a no start diagnosis. And I've seen other manufacturers do the same thing. Just be aware of it. As far as the Ford EEC power relay, and that stood for electronic engine controls. Let's go down to that figure on page 4. And what's unique about this one was Ford decided to use a relay to power up, that's this EEC power relay, use a relay to power up everything under the hood. So a typical design would be, say, purge solenoid, vent solenoid, EGR solenoids, fuel injectors, ignition coils, and certain relays would be powered up when you first turn the key on. So from the run circuit of the ignition switch, that all of those loads would come into play. Well, what Ford did was they used a relay to do that. So rather than having the ignition switch carry all those loads, so let's say that this is the run circuit of the ignition switch, and it's going to feed circuits all over the car. Like I said, all the relays, injectors, coils. What Ford did, instead of using the ignition switch like this, is they just added a relay in the picture. And what the ignition switch did was control the control side of that relay. So the relay itself, this went to battery positive, and you can kind of see that in my picture. But what this did is all the loads would come from the battery and feed all these circuits instead of the ignition switch. So the ignition switch, instead of carrying that 40 amps of current flow for all those circuits, now only carries 100 milliamps to energize the control side of a relay. It took that load away from the ignition switch. So I put that one in there because you have a bad power relay on a Ford and nothing works. It's like having a bad ignition switch. So it's a unique design. What else is unique about it is you have the load side of this EEC power relay controlling power to the control side of the fuel pump relay. And so why am I talking about this within the fuel pump circuits? Is you can have a bad EEC power relay that's causing a no fuel pressure problem. So it's kind of weird. Load side of one relay controlling the control side of another relay. That's Ford. Something else in this picture we can talk about while we're here would be the inertia switch. An inertia switch on Ford's, two manufacturers I've seen inertia switches on. That's page 5. The two manufacturers I've seen inertia switches on would be Ford and Hyundai. And these were developed as an extra safety measure in case of an impact, in case of an accident. And what you had was a magnet here that would hold this weighted steel ball in place. And in case of an impact, what would happen is that steel ball would leave its position on the magnet, it would strike this plate, and it would open up these fuel pump contacts right here. So it was a mechanical piece. And I've seen vehicles come in with, a trunk full of groceries. Obviously, somebody slammed the trunk lid too hard, tripped the inertia switch, vehicles towed in. You see other cars that have a ding in the bumper. They just backed into something. They don't realize it's there. I had a student with 15-inch subwoofers in his trunk. And, his audio system was tripping his inertia switch. You got to look for those. You certainly wouldn't want to put a fuel pump in a car when it had a bad inertia switch. This is what it looks like on the diagram, and you can see that it is in series on the load side of this fuel pump circuit. Another option that they use is they put the inertia switch up here, which would put it on the control side of the, sorry, that would still be load side. It would be on this side. I've seen them on this side, either here or here. So that would put the inertia switch on the control side of the fuel pump relay. And in either case, it's going to be interrupting power to the fuel pump in case of that accident. Now, what's nice about these ones on the load side is if you know where they are, which on the cars are generally in the trunk area, and on the trucks are in the kick panel or the right side, usually passenger side. But that's the load side of the fuel pump. So if you want to do a fuel pump current test like we were doing yesterday, looking at our amperage waveforms, you can just click your amp probe right around the wires to the inertia switch. So it makes it nice. Some of the newer cars are actually putting a light on the dash if the inertia switch is tripped, which was nice for the owner of the vehicle. But look for those. For example, a Hyundai that I looked at not too long ago, one of the garages I worked for, it was a no start, it was a body shop. It was a Hyundai Santa Fe, and it had a subframe put in it, so all undercar damage. And the car wouldn't start. Now, unfortunately on this car, checking fuel pressure was not easy to do. There was no Schrader valve on the rail, so I couldn't adapt the pressure gauge easily. The car wouldn't start, had good spark, shoot some carb clean in the intake, fires right up. So I know it's a fuel issue. I got to check my fuel pressure, but I can't do it. I don't have the right adapters. So I grabbed the wiring diagram because I'm going to do power and ground checks on the pump instead of pressure. I grab the wiring diagram, I look at it, I'm trying to find my pump connector and relay and all that, and I look on the diagram, and it had on the diagram one of these listed on the diagram. Body shop, new subframe, accident. Find the inertia switch. It's under the hood next to the left front strut tower. Very difficult to see. It wasn't colored like some of these Ford ones have a red button on top. This thing was black and very difficult to see. It was tripped. I reached down, hit the button, car started right up. Something to look for. It's a good money-making day for me that day, right? All I had to do was click. I'm done. Thank you very much. Have a nice day. Okay? Look for inertia switches. The oil pressure switch that GM uses. I put this one in here because this is the most widely this system, it has so much misconception involved with it on why it's there. So let's go down to page 6 and take a look at why this thing's here. Again, generic picture, GM oil pressure switch. And a lot of people think that this oil pressure switch, which is right here, is here to shut the engine off if the oil pressure gets too low. That's completely false. That is not why it's there. We are not trying to protect the engine with this oil pressure switch. If you look at the circuit, what you will see is this is a parallel branch to the fuel pump relay circuit. It's not a series branch, it's parallel. By parallel means two separate paths. Series means they were tied together. So what happens is, if either one of these two blue lines that I just drew right here, if either one of those has power, that pump's going to stay running. Okay. So regular relay circuit first. We'll get back to the switch. What you see on the coil, which is the control side, is an external ground. So we've covered this. That means inside of the computer is a power side switched driver. So this would be a positive feed. Computer controls the power of the control side of the fuel pump relay. It would work like every other one. You turn the key on, you get a 2-second prime. Pump shuts off. Computer needs an RPM signal to turn that thing back on. Energizes the coil. As long as the coil is energized, this switch is going to stay closed. And what we're going to have is 12 volts coming down to my fuel pump circuit. The pump's going to be running. Okay? At the same time you started that car, it has built oil pressure, and this is a hydraulic switch. So this switch right here is going to close with oil pressure, and you have a separate parallel branch of power that can go to the pump. Why did GM feel the need to do this? I don't have an answer for that because nobody else was doing it. It was there to back up the relay in case the relay failed. It's there to back up the relay in case the relay fails. So, I guess GM had a bunch of problems with their fuel pump relays early on, and they had something that they just felt that they needed to keep forever. I don't know why they do it, but it is not there to shut the car off in case we lose oil pressure. Now, here's what's unique about these. Let's say the car comes in, and I've seen this. It's a no start, and it's a no crank. Do your diagnosis, you find a bad starter. Put a new starter in the car, and what you find is an extremely long crank time. You crank it over for 15 seconds, you crank it over for another 15, of course waiting between, let the starter cool down. By the third 15-second crank, the car finally starts. The reason the starter failed in the first place is the owner of the car has been driving it that way for a long time. So you mention it to the customer. Do you want to do something about that? Protect your investment? Of course they do. They just spent a couple $100 on a starter. And what you find is a bad fuel pump relay. The car was actually starting through the oil pressure switch. When the oil's real thick and cold, it's hard to build up that 4 psi of oil pressure when you're cranking. So what will happen with a faulty fuel pump relay on these GMs, the car will still start and run, but when the engine's cold, you will have an extremely long crank time. When the engine's warm and the oil is thinned out, you can build that 4 psi oil pressure pretty quickly, and the car starts almost normal when the engine's warm. So look for that symptom on GMs. Extremely long crank time. I'm not talking about an extra second or two. I'm emphasizing the word extremely, right? Because you'll have that. So look for that. That's going to be one characteristic. The second one is this, and this one's even more important. When it comes to fuel injection services, okay? A fuel injection service, what we're doing is we're taking that fuel rail that contains all the injectors, and we're putting in the Schrader hopefully a test port. Well, GMs definitely have this right here. We're putting a pressurized container mixed solution of gasoline and some kind of cleaner when we're doing the injectors. And when you do a procedure like this, you have to make sure that this rail holds pressure on shutdown. Okay? For example, let's say that here's our fuel lines. They run back to the tank, say a return type system, and you put a gauge on this, and your gauge is dropping when you shut the key off. What that means is when you put this pressurized container, and when we try to run the car off of this instead of the pump, you're going to push all that solution either back on the pressure line or back on the return line, so your regulator being here, back on the return line, and you're going to not be able to clean the injectors like you're supposed to be. It's going to push that solution back to the tank. Okay, so it's a bleed down problem. We'll address this later, but let's say that your fuel pump check valve is leaking, which is a common issue. Let's say the pump itself, the check valve is leaking. So our bleed down is occurring here. If we pinch off this rubber fuel line right here, we can prevent the gauge from dropping. So now let's say it holds at 30 and is not dropping anymore. We can do our injection service now. Okay? So we're doing a fuel injection service, and we remove the fuel pump relay to keep the pump from running. Obviously, you'd want this pump to shut off. You would not want the pump running and pushing fuel up to your pair of needle nose vice grips that you have pinched on that line. Because some of these injection services, you'll run the car for 20, 30, 40 minutes before it runs out. Again, this is an externally pressurized container. It takes a while for this to run down, and the car's going to run for a half an hour. Imagine running a fuel pump for a half an hour up to a pair of vice grips, and it's basically a dead-headed situation. You're going to burn the pump up. And you're thinking, well, the pump's off because I have the relay in my hand. Not on the GM, because what's it going to do? It's going to get power through this oil pressure switch as long as the engine's running. So it's important to know that this oil pressure switch is there in this situation too. The only sure way to disable the fuel pump on a GM is crawl underneath the car and unplug it at the tank. Then you can do your injection service. So that's why I mentioned the GM when it's unique. It is completely described incorrectly in this field. Everybody thinks it's there to protect the engine from low oil pressure. That's not why it's there. GM oil pressure switch. Okay, something else I missed. Let's go back to that. There's something else unique that GM uses, and we were doing this yesterday on one of the cars we were working on. They provide a fuel pump test port. Now, again, I don't know what the intention was with GM to have this, but it's nice to know that it's there. Situation that you're going to run into a lot is the vehicle's going to come in and it has no fuel pressure. It's a no start. And before you ever put a fuel pump in a car, you would always want to check your power and check your ground in a loaded situation. And when I say loaded situation, that means that the circuit is active and alive, the relay's closed, you're sending 12 volts down to the pump, and so you check your feed, and then your ground, you want to see, 300 millivolts or less, something like that. That would be a good ground. Loaded circuit's the key. The problem with doing that is the car doesn't run. So to have a loaded circuit with the relay, you have to have an RPM signal. And so you get your buddy in the car, and he's cranking it over for you while you're underneath the vehicle trying to find a good ground on that rusty frame. So you can't find a good ground, and then you're trying to locate the wires because there's multiple wires. And by the time you locate a good ground and the correct wire, you've overheated the starter and killed the battery. Not to mention your buddy inside the car is pretty pissed at you because you're taking too long. He's got work to do, and you got him up in the air. So what we need to develop when it comes to fuel pressure testing, and what we need to be able to do is confidently energize the circuit manually, and then we don't have to crank the engine over anymore. We can do our pump, power, and ground checks without doing that. So it's nice that GM has this, because the way I do them, I'll put a jumper wire, fuse jumper wire, directly to battery positive, to the fuel pump test lead. And what that's going to do is put power to the pump. And now I can do my loaded circuit tests without cranking the engine over. And I got the car up in the air. I don't have anybody in the car. I can take my time, right? And then we can check it. So it's nice. So if the car comes in, again, it doesn't start, and you have no fuel pressure, and you jump this circuit, and now you have fuel pressure, now you're going to focus up this way. But if we still have no fuel pressure, you're definitely down here, but it's nice because you don't have to crank the engine over to do it. So along those lines, I want to show you one more. All right, before I show you that other one, question I just had was checking this ground. If I had a bad ground, would I read high volts? And the answer is yes. But the key with checking that ground using a voltmeter is the circuit must be loaded. If this ground is broken, say right here, and you check this ground with a voltmeter, and it would be connected like this. One lead to the frame, the other lead to the ground itself, you're going to read 0 volts. Of course you're going to read 0 volts. It's ground to ground testing. But the key is you have to have the circuit loaded. If the circuit's loaded, that means you have 12 volts coming in this way. If you have 12 volts here, now what's going to happen is your voltmeter is actually going to read 12 volts right here with a bad ground. You will read 12 volts right there. The key was circuit had to be loaded. You can't check that ground. You cannot check this ground unless you have power feed coming in here accurately with a voltmeter. And so, yes, that's the way you check the ground. If the ground's bad, you're going to have an elevated voltage. And I'm saying for a fuel pump, electric motor, 300 to 400 millivolts would be the most you'd want to see. You start seeing 1, 2, 3, 4 volts or whatever, you're going to have an issue. Actually, real quick case study I did, low fuel pressure on a car. 9 times out of 10, low fuel pressure, you're putting a pump in it. But always do your checks. And this was a former student's car, and I needed to be 100%. When I checked the pump ground, I had 6 volts on the pump ground. And what happened is this vehicle was in an accident, had some body work, and the bolt that holds the fuel pump ground to the inside trunk area was loose. All that car needed was the bolt tightened up. This student was very happy with me in handling that for him because it didn't cost him any money to have a fuel pump put in it. So be careful. Again, loaded circuit, voltage drop testing is the key. All right, let's look at another one. The circuit opening relay that Toyota uses. The only reason I pulled it up again is just to show you guys what we can do with energizing pump circuits. And this is a Toyota design, and I'm pointing these out in the picture on the data link connector under the hood. And I don't know if they still use this in the OBD2 cars, 96 and newer or not. I think they did. You could take a jumper wire from the FP pin to the B plus pin, and what that would do would be directly power from the main relay. It would directly power through our jumper wire our fuel pump circuit. So again, you want to measure fuel pump current like we did yesterday, you can put a jumper wire in there. A couple different things we could do. Put your jumper wire in there, put your amp probe on your jumper wire, put that to your scope, and you can measure the fuel pump current right from the data link connector. That's wonderful if you're working in the driveway and it's gravel driveway and you want to lay on the ground. You can do it from the front. So I'm pointing that out in that picture. And this is that Toyota also that used what they call the circuit opening relay. And this tied in with the vane airflow meter that See, I wrote VAF on older systems. The way that worked was this wire came to a contact switch inside the vane airflow meter, and that switch controlled the ground. So you can see that if this was the VAF switch, that there's no computer involved in this relay. We still have a fuel pump that we need to run, and we still have safety issues that we have to deal with. And that safety issue is if the car stalls, when you get into an accident from a severed fuel line, we need the pump to shut off. So if the computer's not controlling that, it was still done, but it was done with a VAF switch. And the way the circuit worked was during cranking, and that's this starter relay down here. During cranking, this switch provided power to this coil. So during cranking, it actually was done through the starter. The starter circuit, during cranking, would energize the control side of the relay, would latch the switch, and this coil would get power. But as soon as you let off the key, this would no longer be there. This coil would collapse, because again, this comes through the start circuit. But what happened in the process with the car starting is the airflow meter opened the door, which closed this switch and provided a ground for this coil. So now when this one collapsed, this coil takes over, closes the switch, and the fuel pump is now running through that all the time. If the car gets into an accident, like I said, sever a fuel line, the car stalls, the airflow meter switch opens up because the door shuts, and that shuts the fuel pump off. So there's your safety feature. We talked about that before. The VAF fuel pump cutoff switch in the Toyota 7-wire VAF sensors. All right, so just wanted to point out some differences in designs. Some common components that you're going to run into, some things you need to think about is why this page is here. So going further, we're going to cover some other circuit designs. And page 8, we'll start with this one. Just some other things to think about when you're dealing with fuel pump circuits and no fuel pressure. Some systems use variable voltage controls to their pumps. And who would have thought a 92 Jeep would have a variable speed fuel pump? But it did. And the symptoms with this Jeep when it came in was you cranked the engine over and you had fuel pressure. And then you let it off the crank position because the car started and fuel pressure would just drop all the way down to 0 and the car would shut off. And you'd re-crank it again and you'd have fuel pressure, let the off the crank position because the car started, and it would drop all the way down to 0. Looking at the diagram on this car is kind of crazy. I've kind of pulled everything out of it to make this clear. Hopefully it will be. But if you look up top, I'm looking right here, the auto shutdown and the fuel pump relay. Remember I told you just a minute ago, they separated the two, but they used the same control wire to the PCM. So my blue dotted line up here is showing that these two relays, that's right here and right here, are being controlled by one driver in the computer. Okay? Computer controls those relays, powers everything up. Okay, from there, let's look at the fuel pump, see where it gets its power from. We can start right here at the tank unit. And if you look at this pump, what I do generally when I'm starting a wiring diagram and figuring out what's what, is if you look at this, you look at this side of the pump and you can see on the diagram itself that it says it goes to a ground. So if that's the case, this side right here is power. So our pump is going to run on this dark green and red wire. This is going to be our power feed to the pump. Okay? If you follow this diagram, you follow this power feed over, you will see a splice right here. And this splice is what's going to provide the pump with two different speeds. Notice just to the right of this, I'm looking right here, there is a ballast resistor. Like an old school ballast resistor used on an ignition coil system that you'd see on this vehicle. It was mounted on the left front inner fender. It looked just like an old school ballast, but it had nothing to do with the ignition coil. It actually was a resistor to reduce the power to the fuel pump. So there were two ways that we get power. One was through the ballast, which would provide a reduced power, and the other one was through this ballast resistor relay, which would provide full power. Do a little description operation on the vehicle, you find out why are they doing this, and within the description it actually says right here that it was only done to reduce the noise of the fuel pump. And in '93, they didn't do it anymore. They just ran it like every other car. So it was just for noise. And the weird part about it was, well, not really weird, it kind of makes sense. During cranking, would you want to reduce the current flow to a fuel pump during cranking? Of course you wouldn't. Your battery voltage is already low. Why would you want, and it's low from the starter, why would you want to reduce it any further? So we don't want to reduce voltage to the pump during cranking. So we're going to go around the ballast and we're going to send power to the pump through this relay. So we're going to go this way and we're going to send power this way during cranking. But as soon as you let off the crank position, on this design, what it did is this relay would open and then we'd send power through the ballast. So now think about the symptoms. Crank, start, run, stall. That's what it would do every time. Crank, fuel pressure, it would start. Fuel pressure drop, it would stall, and what was happening was a bad ballast resistor on the car. That was what was wrong with the car. So be careful. Again, system designs, you have to be aware of things like this. I had another one that was very similar. This is a 3800 supercharged 3800 supercharged GM, and with the supercharger, obviously we have a higher fuel demand, so it would make sense that the supercharged 3800 had this and the regular 3800 did not. They put a high volume pump in this thing, and it was almost too much fuel unless the supercharger was up into play, right? So low speeds, they would run the pump at a reduced voltage. And at high speeds, when the supercharger's in place and we need a lot of fuel, we need our pressure to be maintained higher, it would bypass the resistor, and it would, just like the Jeep that I just mentioned to you guys, it would bypass the resistor and it would apply full voltage to the pump. So again, same exact symptoms. And this was a car I worked on, got good pressure cranking, but then the car would stall. It would not stay running. Crank it, good pressure, and then as soon as you let off the crank position, fuel pressure would drop down, the car would stall. Same exact thing. If you look at this, there is a fuel pump resistor, two-speed pump. The pump's right here. I kind of pieced this picture together. It's kind of tough to pick it out, but you can see on these systems that they're using two relays again, just like on the last picture. They were using two relays to do this, and it really comes down to being able to read a diagram. Here's one, it's a ballast resistor relay, and then of course your second one's your fuel pump relay. You start seeing multiple relays, that's a red flag that's what they're doing, running two different speeds. But if you look at the circuit, on this one, got a fuel pump speed control relay, and then I have my regular fuel pump relay. And this speed control relay is going to be, depending on which position it's in, is going to either send the power through the ballast first before it gets to the pump, which would be this way, or if the switch is the other way, it would look like this. If the switch was over this way, what's going to happen is we're going to get direct power to the pump. So you can see that that relay, this speed control relay, is going to be, this path would be no resistance, right? And this path, if it was switched this way, would be high resistance to the pump. Why am I mentioning this? You know, every car is different. You guys need to be aware of different fuel pump circuit designs. In the later model, same car, they got rid of the resistor. Why'd they get rid of the resistor? Because the resistor had all kind of problems. So now what they did in the later model, same car, it's an updated version. They still use a variable speed pump, but now we're doing it on a pulse width modulation control module. Instead of using a resistor to drop the voltage to it, you see this fuel pump control module is controlling the pump power and ground right here. And now it's pulse width modulated, duty cycle controlled, and we'll pulse the motor on and off to control the speed. You have to be aware of this kind of thing when it comes to no or low fuel pressure. Different circuit design. And then our electronic returnless systems, which were crazy, they added a fuel pressure sensor to the fuel rail on these designs because there's no fuel pressure regulator. So it was important that the engine computer was able to monitor pressure. I mentioned to you guys about this pulse dampener looking like it is a pressure regulator. So I pulled this up here because major confusion on that dampener looking like a regulator. It's kind of crazy because it had a vacuum hose going to it too, right? And the vacuum line on that regulator or dampener, fuel spillage, that was all it was there for. But on this system, it was the same kind of thing. You have a fuel pump driver module in the tank, and that fuel pump driver module is controlling the pump speed by a pulsed on-off signal, variable duty cycle. Alternate designs you guys have to be aware of when you have a low pressure problem or no pressure problem. It could be a pump, it could be the module, wiring, inertia switch, the computer. You have to know what you're dealing with. I've added another system in here. We can do this one later. 2000 Ford Contour. It was just a case study. And what I've done is I've put in basically what you're looking at, the commands to this, and what kind of signals you're going to see on those circuits when you're checking them. But I'll do this one later. We'll talk about this when you guys get a break. Kind of a crazy system, but I got pressure in here and frequency and duty cycle, and I put these in here really just so if you guys ever run into one of these, that you'll have some kind of idea of what you should be seeing on these wires. And it pretty much walks you through where I'm connected on it, so you can plug them in. All those pictures are going to apply to this diagram here on page 12. All right, fuel pump electrical circuits. It's not just as simple in some cases as just a power and a ground tech. You can have variable speed pumps. You can have resistors dropping voltage. You have to know how to read a wiring diagram. That's going to be key. And it isn't just as simple as low fuel pressure or no fuel pressure. Oh, let's put a pump in the car. Granted, maybe 80, 85, 90% of the time when you have low or no fuel pressure, you need a pump, plugged up filter. But there's that 15, 20% that you're going to run into electrical problems. And truthfully, doing diagnostic work, being 80%, 85% is not good enough. You need to be in the upper 90s. You have 2 cars come back for every 10 you look at. That's not a good ratio. You have 2 cars come back for every 100 you look at. That's better. That's where we need to be. So we need to be thorough. Fuel pump electrical circuits.